Okay, so today's plan is to go through those three problems in the midterm. Actually, the first two problems are very similar to what we did in the last discussion section, right? So the first one is basically given the state of equation and ask you to calculate various functions like entropy, free energy and energy stuff like that. And the second question, given this PV diagram, ask you to calculate the efficiency. So the problem three, I'm pretty sure the professor did one-dimensional harmonic oscillator in the class, right? And also there's homework, I think. Yeah, it's just a three-dimensional version of the problem. Yeah, so let's start from the first one. Also feel free to stop me if you have any questions. I think it's week 5 or I think it's week 5. Problem 1. Okay, so the system is a rubber band without any force. The length is the L naught. So when the length is L, the force is given by A, T is a temperature, A is a constant, a positive constant, and L minus L naught, right? So for this kind of by the way, and also you know this, the head capacity, when L equal to L naught is B naught, is a constant. In the first question, you need to calculate entropy as a function of the temperature and the length. Right. This is very similar to one of your homework. Okay, so for this kind of thermodynamic problems, the starting point usually is the energy conservation. We can write down this d, the change in energy, equal to TdS, and usually it's minus PdV, right? In this situation, it should be plus F dL, right? Because if you increase the length, you can imagine that the energy stored in this rubber band will increase. So this should be a plus sign. And from last week's discussion, we know how to calculate the entropy. There are two equations. One is the partial S, partial T, V equal to C V T, and the partial V, partial S, partial V, T, partial P, partial T, V. Now you can kind of identify, F with minus P and L with V. So those two equations would translate into two equations, CL divided by T. The second equation become V become L, T becomes minus F, something like this. So basically, the first equation would tell us the temperature dependence of this entropy, and the second equation tells us the volume dependence. So the the length L dependence of this entropy. Of course, you can derive those two equations from, from this guy, like similar to what we did for this minus P dV. But you can just make this kind of identify those two and just. Okay, so let's look at the first, the second equation. Okay, so because we know the equation, the state of equation, we can calculate the right-hand side of this equation. So F, remember F equal to this guy. So F take a derivative with respect to T would give us minus A L minus L naught. So you do an integral over for this L, we would get the L dependence, which is minus a half L minus L naught, has some arbitrary function of T, which will be fixed by the first equation. Yeah. Is it clear? Okay. I hope it's clear. Just let me know if you have any questions. Right. I will go through very slowly and in very detail. So, okay. To determine this function g, we just plug into the first equation, take a partial derivative with respect to t. We would get this g prime equal to the right hand side is, by the way, we set L equal to L naught, L equal to L naught, because this T is independent of L, so it doesn't matter. And the right hand side is B naught divided by T, right? This gives us B naught log T plus some constant alpha. That's denoted alpha. Doesn't matter. So we know this entropy is given by this expression. That's the answer for the first part. By the way, I think I also posted the solution written by the professor on the CCLE. Yeah, you can take a note. Yeah, that's part one. What is part B? Part B is asking whether this heat capacity depends on B naught or not. Sorry, depends on L or not, right? So we can calculate this CL since we already know this entropy, right? Just according to this definition, which is partial S partial T give us B naught divided by T, which is B naught. So it's still B naught for all the L. That's part B. Yeah, part B. Okay, so if no question, I will keep going. Part C, we need to calculate, we need to figure out what is the energy as a function with T and L, and what's the free energy as a function of T and L. So we know how to figure out, we know how to do this energy, right? Because, from what we discussed last time, we can also write down two differential equations for this energy, which is partial E, partial V, T equal to T partial P partial T V minus P, and also partial T partial T, which is CV, right? And we do the identification that V becomes L and P becomes minus F. That would give us the first equation becomes partial E partial L T minus T partial F partial T L. Minus P becomes plus F. The second equation becomes partial E partial T L and CL. That's basically those two equations you need to know to calculate this energy, internal energy, right? So we can also calculate the right-hand side of the first equation from the state of equation, right? So F equal to AT L minus L naught. So you take a partial derivative, you get A L minus L naught. And you notice that the right-hand side of this first equation vanishes, right? It's zero. You just plug in this first term is minus T A L minus L naught. The second term is A T L minus L naught. So it's zero. So basically it tells us the energy is independent of L, right? So the energy is only a function of temperature. And from the second equation, we know it's B naught. The derivative of temperature is B naught. So we know the energy, the expression for the internal energy is B naught T plus some constant. Let's denote alpha prime. Something like that. Right? Since we know the entropy and also the internal energy, we know what is free energy. Free energy is given by energy minus Ts. You just plug in the expression of plug the expression of E and S into this expression, into this equation, you would get the free energy. That's all for the part C. Yeah. So any question? Okay.
One question. The constants, at least using this method, are just left undetermined, right?
Yeah, it's undetermined. Yeah, there's no way to determine. It's like tell you the derivative, you never know what's the constant when you do the integral, right? Okay, so for the part, okay, it's part D. What is part D? Part D is, okay, so consider the following adiabatic process. Adiabatic means there's no heat exchange between the system and the environment, right? That means that Q is 0. And we start the rubber band at the extension L1 at temperature T1. So at initial time T0, the temperature is T1 and the length is L1. They are given and let it go. Eventually it will turn back to the original length L0. So basically let it go. So basically it's like you hold this rubber band with your hand, then just release it, right? During this process, there's no force acting on your rubber band. meaning that the work done on the system is also zero. Now you need to calculate the temperature difference between the final state and the initial state, and versus the change in entropy. So what you need to calculate is delta T and the delta S. So to calculate delta T from this one and this one, and also the energy conservation, we know the internal energy is a constant during this process. So if the internal energy is a constant, and we also know the internal energy only depends on the temperature, that means the temperature is a constant during this process. So we immediately conclude that this delta T is zero. There's no change in temperature, meaning that the final temperature is also T1. Any question about this part, this step?
I kind of have a question. So up at the equation of state, like the idea that this rubber bands gets stiffer with increasing temperature, I think, at least looking back on it, made these things kind of behave unintuitively to me, right? Because like if you warm up a rubber band in like real life, like this effective spring constant, I guess, would get larger and not smaller, or would get smaller and not larger.
Yeah, I agree.
And like this idea of like, a regular rubber band, the idea of like the spontaneous process, like I feel like it would warm up. That's how we sort of understand these things. But like seeing it now, it makes sense given the equation of state.
Yeah. I definitely, in some sense, I agree. Like the temperature, of course, the L dependencies kind of makes sense, right? It's just a Hooke's law. And for the temperature dependence, I mean, it's not obvious it's true. Maybe in some exotic material, it's true. I don't know.
I think I remember we discussed this as like undergrads, and the point is that when you're stretching it, you're actually decreasing entropy, if I remember correctly, because they're aligned more than they would be if it's unstretched. That's why it's a little bit like counterintuitive.
Yeah, maybe, I don't know. or you can think of in general, it's a function of T, and in you do tiny expansion for some material, the median order is the it's a linear term, whatever, something like that. Yeah, anyway, it's just it's given. Of course, if you want to think of like a real systems to make it more physical to you, I guess you need to do more search, think more about it. That's a good question. Yeah, basically, but for our purpose, it's quite we don't need to care about it, like, just for example. Yeah, okay, so let's back to here. Okay, so we know the initial L and T and the final L and T. Of course, we know what is the difference in delta S, because S is a function when T and L, right? So we just write the change in S is given by S. The final one is L naught T1 minus the initial one, which is L1 T1. We plug in, we know the expression for the entropy, the S. We plug in of course, the constant cancel out because you have the same temperature. So this the second term also cancel out. So you basically you only have the first term. The first term. So this guy is 0, right? Because if your L is L0, then the first term also vanish. So only left with we only have the last term, and this minus sign cancel with the minus sign here. So we have it's positive. The entropy is increasing. Yeah, so that's the part D. I hope it makes sense. Okay, so for part E, it's very similar. The only difference, instead of just release it and let it go, here we hold this rubber band and make it shrink very slowly. It's like it's a very basically means it's a quasi-static. Now you have a force kind of holding this rubber band at some when it's shrinking, right? So the external force is external work is non-zero. That's what you need to calculate. But because it's a quasi-static, we have an extra condition, which is delta Q equal to T delta S, which vanish, meaning that in this process, there's no entropy change. Right. And from this condition, by the way, we work on T1 and E1 and sorry, L1, T1 and L0. We don't know T0, but from this equation, we can figure out the T0 as a function of other parameters. Right. Basically, we have S L1 T1 equal to S L0 T0. We can solve for T0. Once we have T0, because the dE equal to delta Q plus dW. dW is a work done on the system. It tells us delta W, the work done on the system, equal to the change in the internal energy. The change in the internal energy equal to the final internal energy T0. Remember, the energy only depends on temperature minus T initial. And we also know T0, right? So we just plug in to figure out this work. That's the logic to solve this problem. And I mean, this just kind of algebraic equations. You can solve it very easily. It's given by it's a T1 exponential minus A L1 minus L0 square 2B0. And this is B0 T0 minus T1, something like that, right? You just plug in, you get the result. That's the problem 1. Yeah. Any question about this problem? Yeah, I actually think this problem is a very nice problem as a thermodynamic problem. Okay, so if no question, let's go to problem 2. Okay, so problem 2, basically it's a cycle it's like, okay, so it's we know the PV diagram. We have two adiabatic line. And this is V1, I believe V2, and A, B, C, D. So the first one, we need to figure out the equation of the adiabatic lines. I'm pretty sure everyone knows it's just P V gamma equal to constant. Yeah, I believe everyone gets this problem, this part right, because that's derived in class, I think. And the part B, you need to calculate the entropy, sorry, the efficiency of this process. It's an engine, right? We know the efficiency is given by 1 minus QC divided by QH. QC is the, okay, so it's the engine. QC is the heat the system released to the environment, and the QH is the heat that is absorbed by the system from the environment. Since from A to B and C to D are adiabatic, meaning that there's no heat exchange. So the heat exchange only happens in B to C and A to D, so D to A, right? So let's focus on those two processes. From B to C, the heat exchange is given by, because it's a fixed volume. Fixed volume means, according to the definition, is given by CV, right? TC minus TB. And from D to A, very similar, it's a fixed volume process, the TA minus TD, right? And C minus B, TC minus TB is a negative number, and TA minus TD is a positive number. So negative, I believe so, right? Yeah. Negative means it's releasing energy to the environment, right? Because this delta Q is in DE delta Q. So this guy is negative, means your internal energy is decreasing. Decreasing means it's giving energy to the environment. So this corresponding to the QC, and this corresponding to the QH. By the way, QC is the absolute value of this guy. So we only need to figure out this CV, TB minus TC, CV TA minus TD. Right. Yeah. So for, is everything clear? Okay, this step is very similar to what we did in last discussion. We first convert this temperature to the volume, and to the pressure or the volume, the pressure and the volume. And then to do that, we just need to use, we just need to invoke the because it's ideal gas is PV equal to NKBT. So meaning that temperature temperature is given by PV divided by constant. If we plug in, this constant will cancel out. So we can just replace T with PV. And it's B. VB is V2, right? VB is V2. And the PC, the volume is also 2. And this is a PA, the volume is V1, and the PD, volume is PA. So it's 1 minus PB minus PC, PA minus PD, V2, V1. Right, so from this step to this step, we only use PV equal to NKBT. And from this step to the final answer, we only need to, I believe, with something like gamma minus 1, something like that. We only need to use the PV gamma equal to constant. Right. Basically, we need to connect the PB with PC and the PA with PD. To do that, or should be PA with PB and PD with PC. So that can, PA V1 gamma equal to PB V2 gamma. This point equal to this point, and the PD V1 gamma equal to PC V2 gamma. And plug this relation into here, and you will find this pressure cancel out, and only left with, we only have this V1, V2 dependence. That's how we solve this problem. Any question about this problem? Problem 2? Okay, so if we have no problem, let's look at the problem 3. So first is a quantum harmonic oscillator. I'm sorry, it's like the wording is not very clear. Yeah, it's a quantum harmonic oscillator. It's a 3-dimensional. So it's something like this. Something like that. And the first one asks you to calculate the partition function in an easy way. So so easy way here means it's basically it's a 3 independent 1-dimensional harmonic oscillator, right? Because in the expression there's no x, y, this kind of cross term, meaning that those 3 harmonic oscillator cannot exchange information and energy with each other, meaning that they are basically independent. And so they equal to the 1 to the cube, which is what's that? So n equal to 0, from 0 to infinity, beta h is n constant, something like that. And you can do this sum. This sum is easy to do. There's a constant due to this 0 motion, 0 energy, yeah. Okay, which is this guy. And there is also a sum from 0 to infinity. You think of this guy as x, so it's 1 divided by 1 minus the x. That's the answer. Yeah, I believe some students treat this as a classical harmonic oscillator, Yeah, but should be doing this in this way. I take 2 points off if you do it in classical harmonic center, but you get most of the points. Okay, so yeah, I believe this part no problem. Or the problem should say more straightforward way. It's just anyway. Part B, do it in a hard way. You need to consider the degeneracy, stuff like that. That basically means you need to, the energy is X plus Y plus Z plus this guy. We call this guy N. So the energy is only a function of N, right? By the way, this N here is different from this N here. This N is only for one harmonic oscillator. This N is the sum of 3 harmonic oscillators. So now for N equal to a finite integer, there are various ways to to arrange, and for example, N equal to 1, X, I can choose the first harmonic oscillator to be 1, the second and the third to be 0. I can also choose my second to be 1, and I can also choose the third to be 1, meaning that there is a degeneracy. Here is the degeneracy is 3 for N equal to 1, right? And that's so there should be a degeneracy, which is a function of your energy levels. Sorry, it's a function of your energy. So basically from, okay, so originally you can also write in this way. And let's so here is summing over the microspace. So here is summing over the energy, your energy of the system. That's very similar to what we usually say in the solid state. It's like you have an integration over the Brownian zone, the momentum. Sometimes we convert this guy to the integration of your spectrum, your energy. That's basically what we're doing here. And then there's a, there's a density of state, right? And now we need to do this guy. First, we need to figure out what is the degeneracy. So the degeneracy comes from this one, right? For fixed integer n, there's different ways to achieve that. You can think of it as like m points. And now you need to separate m points into 3 parts, right? Meaning that you need to insert 2 separators into those m points. You can insert your separator here, meaning that there's a 0 in 3 values, and you can also insert here, and that means the position of that you can put place your separators m plus 2, right? I believe so. M plus 1 or m plus 2. M plus 8. 1, 2, 3. Wait. should be 1 plus 1 plus. The final degeneracy is, I know the final degeneracy is given by this guy, I think. Because n equal to 0, there's no degeneracy, right? 0, 0. And n equal to 1, there's 3, degeneracy is 3. But where goes wrong here? And I see, right. If n equal to 0, if n equal to 1, if n equal to 1, I can put my first here or here. I think the point is when you place your second separator, you can place it at the same position of your first separator. That would increase 1 position for your like place of placing your separators, right? Another way, by the way, another way to figure out this degeneracy is just, you know, if you fix your nx, your nx can be 0 or n, right? Then how many choice you have for ny? You can do this way. This way is more rigorous, like more, I guess it's you have a less possibility to be wrong. And ny plus nd equal to n minus nx. That means your ny can be 1, so it can be 0, 1 to n minus nx. So ny has n minus nx plus 1 choice, right? Once you fix your nx and ny, your nz is fixed. So the total degeneracy as a function of n is given by your nx. Nx can be 0 to n. And for a fixed nx, how many choice for your ny is n minus nx plus 1. That would give you the degeneracy. This one is more rigorous, I guess. Yeah. That is easy to do, right? So summing over nx equals 0 to n. This guy minus nx equals 0 to nx. This guy is a constant, so it's n plus 1 squared, right? Minus this guy is what? 0 plus n times n plus 1 divided by 2, right? I mean, it's just a summation of like 1, 0, 1, 2, 3. We learned in, I guess, n plus 1. That would give you the correct answer. Something like that. Yeah, I believe this one is correct. Right? N plus 1 factor out, you factor out this minus n, this is 2, 2. So it's given by 2n plus 1 becomes plus 2 on the this guy is correct. Yeah, any question about this degeneracy? Okay, so once we have the degeneracy, we just insert into this, insert here. So the sum we need to do is n equals 0 to infinity of n plus 2, n plus 1, exponential minus something like that, n plus. So this kind of sum is very standard, I guess. You need to, you know the trick. We denote this as A. Let's denote as A, or there's no A in this problem. Okay, denote as A. Then the sum you need to do basically is n plus 2, n plus 1, minus beta n. Right. So to do that, I believe in professor's solution, you just expand this. It becomes n squared plus 3n plus 1. You can do each term. So for this one, you can take the derivative twice, and this one you take the derivative once with respect to the a, right? This one you just do the sum, but you can also do it another way. By the way, you can also add a 1 here, right? It's just a constant. You can back it out. Then it's this guy is given by partial minus a, sum over n equal to 0 to infinity, and minus 2 exponential minus a as well. And so what's this guy? This guy is given by first we do a trick. So I change this 1 to 2. Then I need to multiply a exponential a, right? So this guy is given by I put this exponential a to here, and so n plus 2 and the partial answer. Yeah. And we know what this guy is. This is just 1 over 1 minus exponential minus a, exponential minus 2a. And just do the derivative, you would get the same answer. It's just a mathematical trick. Yeah, whenever you calculate, if you have an integral, it's like alpha exponential minus a alpha, d alpha, you can treat this guy as some derivative with respect to a, and do the easy integral first. And same thing here. Right. I think the time is up, but that's almost the problem 3. The difficult part, I think, is the sum, and also how to figure out the degeneracy. Once you have the partition function, in principle, you can calculate everything. Right? You take a log minus t, something like that. You get a free energy. For the entropy, for example, you just like that. Oops, temperature. And you know this guy, and you know this guy, you know what is energy. And you know energy, you know entropy, you can verify the third law of thermodynamics when temperature goes to 0, and the entropy also goes to 0 in this situation, because the ground state is unique. There is no degeneracy in the ground state, meaning that it's like this is the ground state 0, 0, 0. This nx, ny, and z. The first excited state is 0, so 1, 0, 0, 0, 1, 0, 0, 0, 1. This is threefold degeneracy, but the ground state is unique, meaning that if you calculate the entropy directly for the 0 temperature, it will give us 1 minus 1 log 1, which is 0. The probability stay in the ground state is 100%. There's no other choice. Yeah, that's all I want to say, I guess. Any questions? Okay, I guess that's all for today, and feel free to go if you have no questions.